Hi everyone, Mr. Lee here. In this video I'm going to go over questions 3 and 5. Now just as a little caveat, in the world of physics, these type of questions are like what we want to be at, okay, by calling ourselves like a mastery level, okay. These are the questions where you are given relationships between variables. You're not necessarily given numbers, but you're seeing how one variable affects another. And frankly, that is actually very difficult. It is easy for us to be able to look at the numbers, plug the numbers into an equation, and churn out a solution. And so the next step of mastery is removing those numbers and yet still asking you to go through the same process. This is a skill and technique that we will be using throughout the entire course. And so if you do have any questions, definitely ask. I will be more than happy to help you out on an individual basis. But let's begin. So here is question 3. And what I'm going to do first is I'm going to highlight all the important information. Right? So the skill set that I'm showing you right now is the same exact thing that we've been doing for every single one of these problems. Right? So we know our accelerations. Okay. It just so happens that both accelerations, whatever the value is, it's a. Okay. Now, if this were a word problem, they could have replaced a with a number. So a sub x could have been 5. A sub y therefore would have also been 5. Right? They also give us t, delta d1, v1. They give us, so this is the actual change. So this is where the problem actually kicks in. Okay, so the first part is just the setup. And the setup is trying to show you how the variables relate to each other. And once again, I'll show you exactly what I mean when I am solving it. Now, the second part, this is the change in the variables. So this is where we're actually trying to see how things are being affected. So I'm going to highlight it using different colors. All right. Delta d1, v1, d2, v2. All right, so we have basically two parts of the question. Now, normally if we were given numbers here, we would just go straight to the table and we would solve it. And you know what? I'm going to do the same exact thing here. So I'm going to create my table, xo, xf, vo, vf, a, and t. All right, so here is my table. Oh, there's one tiny piece of information that we gotta remember, rest. All right, so I'm gonna fill in what I know. So we know that the initial position, they don't give it to us, so simply put, that will be 0, okay? 0 meters. Our final position, they give us, which is delta d, so I'm gonna write that in, delta d1. Our initial velocity, we start from rest, therefore we are at 0 meters per second. Our final velocity, they gave it to us, they said it was v1. Our acceleration, now they gave us two, the a and the y, and because they didn't really differentiate between the two, we could just say that a is a, right? There's nothing special about this a, it's just a. And time, of course, is t. All right, so here we have our chart. What I'm going to do right now is actually, I'm going to clean it up a little bit, okay? By that I mean, like, they give us a lot of different things, but I want to consolidate a little bit. So I know my displacement. Okay, so I'm combining these two together. My displacement is just called delta d1. Okay, my change in velocity, delta v, is just called v1. Okay, and of course my a and my t, that's just the same. All right, so from here, I'm going to create my relationships. Okay, so what this means is I want to see how all of these variables relate to each other. And so within the 3 kinematic equations, we can come up with relationships between all 4 of these variables. So I'm going to start off with Vf is equal to Vo plus At. All right. Now, at this moment, what you should do is you should identify what are my zeros. So I know my final Vf is not a 0, so that remains true. My initial velocity is a 0, so I'm going to get rid of that. That's a 0 plus At. All right, so let's just clean up this equation a little bit. Boom. All right, so what we have here is our relationship. All right, now what I mean by this, and this is the skill set that we need to be focusing on, is how do these 3 variables relate to each other? And we can take a look at it by seeing, like mathematically, what would happen if one variable were to remain constant and the other variable were to change. Okay, so I'm going to do a little detour here. So here's my detour idea. Detour. So we have VF is equal to AT. Let's say that our time was the constant, okay, as in the time does not change. And so if that doesn't change, the only two things that we're looking at is VF and A. Now, within the scope of the problem, if our final velocity were to double, so we get 2VF, okay, we want to keep this relationship here. So what I mean by that is I will show you, we have here a 1-to-1 ratio. And the reason we know this is because even though we didn't write the number 1 in front of VF, technically there's a 1. Even though there's no 1 in front of the A, technically there's a 1. So this is a 1-to-1 ratio. Now, you might also hear me call this a directly proportional relationship. And the way that we know it's a directly proportional relationship is if one value goes up, another value also goes up by the same value. Okay, and also it's on opposite sides of the equal sign, and they're both in the numerator. So we have a 1-to-1 ratio. So if my velocity increases by a factor of 2, so does my acceleration. 1-to-1 ratio. If my acceleration increases by a factor of 4, so does my velocity. It's a 1-to-1 ratio. Okay. All right. Now let's do another relationship. So we have a VF is equal to A and T. So let's take let's assume that acceleration is constant. The acceleration does not change. Okay. So if that is the case, we are looking at how VF and T have how they relate to each other. All right. So here's my relationship. They're on opposite sides of the equal sign, and they're both in the numerator. Therefore, they are both directly proportional. So what this means is that we have a 1-to-1 ratio. I'll do that in red, just like before. We have a 1-to-1 ratio. Okay, so because we have a 1-to-1 ratio, we can make the following claims. If our time, okay, our time of travel, let's say it increased by a factor of 4, that means our final velocity increases by a factor of 4. 1-to-1 ratio. If our time decreases by a factor of a half, by a factor of 2, our final velocity also gets reduced by a factor of 2. Okay, 1-to-1 ratio is directly proportional. All right, so the last relationship that I want to show you using VF, A, and T is what if they are on the same side of the equation? Okay, so I'm going to use just example numbers here because I think it does a really good job of really showcasing. Okay, so we know that VF is supposed to be constant. All right, so we are looking at the relationship between A and T. All right, what is a relationship? All right. Now, let's give all of these a number, right? So we have 1VF is equal to 1A times 1T. All right, so let's adjust it now. I want my VF to still have a constant of 1, okay? Because we're not changing VF, we're changing A and T. If my A increases by a factor of 2, what must I multiply my T by in order to get this 1? So 2 times what number gives me 1? And that number is 1/2. Oh, that's an ugly 2. 1/2. 2 times 1/2 gives me 1. Okay, so notice I went up by a factor of 2 for my A, and therefore my T decreased by a factor of 2. Now, this relationship still holds true. Let's do 1VF. Let's say we increase my time by a factor of 4. So we have 4T. So what must I multiply my acceleration so that blank times 4 gives me 1? And hopefully we came to the conclusion of 1/4. 1/4 times 4 gives me a velocity of 1. Notice as my T increased by a factor of 4, my A decreased by a factor of 4. Over here, notice how my acceleration increased by a factor of 2, therefore my time decreased by a factor of 2. This is what we call a inversely proportional relationship. Inversely proportional relationship. Oh my goodness. There we go. This is an inversely proportional relationship. And a telltale sign of an inversely proportional relationship is that they're on the same side of the equal sign. All right? All right. So, also another telltale sign is if we were to put one of those variables on the other side, so let's say VF divided by A is equal to T, we can see that the two variables that we're comparing, A and T, okay, the T is in the numerator and the A is in the denominator. Okay, so we have that inverse relationship here. All right, so back to the actual question. We are given this relationship, okay, from the problem itself. Now, what we have to do is we have to see which variables we are changing. So I'll do that over here. According to the second experiment, okay, we increased the acceleration by 2. All right, so we have VF is equal to AT. We increased the acceleration by a factor of 2. All right, we want to see how that affects VF. So V2, so that's my question mark. All right, and notice my T, okay, the time here, it is the same amount of time in the original problem. So my T is my constant. So I don't want to take a look at the relationship of that. All right, so if so I'm taking a look at my relationships here. If I have 2a here, and these are directly proportional because they are on opposite sides of the equal sign and they're both in the numerator. So if my acceleration increases by a factor of 2, my v2 must also increase by a factor of 2. Okay. All right. Now let's see how our delta D is affected. So let's go to our strategies. All right, so once again, our strategy, we're going to take a look at the equations. I'm going to do a little shortcut here. I know which equation to use. XF is equal to XO plus V initial t plus 1/2 AT squared. Okay, at this point, I want to get rid of all my zeros. So I know we have XF, my XO is a 0, my initial velocity, we start from rest, so this is a 0, plus 1/2 AT squared. Okay, now I want to replace my equation variables with the problem's given variables. So instead of saying XF, we know that as delta D, right? And we have 1/2 AT squared. Now, at this moment, we have to actually solve the problem. And remember, the very first step in solving the problem is identifying which variables are constants. So according to the problem, our time is a constant. And 1/2 itself is a constant, so we can actually ignore that. So a relationship that we're looking for is between delta D and A. And according to the problem, okay, we know that our acceleration increased by a factor of 2. Therefore, our delta D, because it's on opposite sides of the equal sign and both variables are in the numerator, we have a directly proportional relationship. If our acceleration increases by a factor of 2, so must our delta D. Okay. So if we take a look at our answers, the answer will be the final one, where our delta D increases by a factor of 2 and our final velocity also increases by a factor of 2. Okay, so we're going to use the same idea to actually answer number 5. All right, so this is question 5. We have a small sphere that is launched horizontally with velocity v initial. So once again, I'm going to be identifying all the important variables that they give us. Now, remember what I said. Usually in a word problem, these variables would be would also have a number attached. Okay, so we have a small sphere launched with speed v toward a target that is a distance d away. The sphere lands on a target that is at a height h, below the height from where the sphere is launched. The sphere were launched again, but with the speed of 2VO. Oops. So this is, I'm going to use a different highlighter because the first part is the setup, okay, and the second part is actually taking a look at the problem itself. All right, so we change our velocity. How high above the sphere would the sphere have to be launched to hit the same target that is still a distance d away? All right, so how high above? That's our question mark variable, right? So how are we changing our height? All right. Now, once again, I'm going to create a chart just so I can organize my my variables here. So we have XO, XF, VO, VF, A, and T. Now, because we are dealing with horizontal and vertical stuff, I'm going to create 2 charts. I'm going to create an X chart and a Y chart because this is a projectile motion problem. So this is my X and this is my Y. All right. It says a small sphere is launched horizontally with a speed of VO. So that'll be here, VO. And it lands towards a target that is a distance d away. So our initial position will be 0 and it lands at position d. Our final velocity, remember the rules, your initial velocity and your final velocity are the same, so we can call that just VO. Your acceleration, the x direction, is 0, and we don't know the time. All right, now for the height, they tell us that our starting height is h, our final height, because we're landing on the floor, is 0. Our initial velocity in the y direction is always 0. Our final velocity, we don't know that. We do know what the acceleration is. Okay, it's negative 9.8, but look what I do here. I'm going to replace that with the letter g. Okay, because g is the acceleration due to gravity. They didn't give that to us, but I want to reduce the amount of numbers that I want to work with. All right, and time we do not know. Okay, so at this moment, what I want to do is I want to figure out time. Okay, because time here is the big determining factor of a lot of things. So knowing all this, remember we usually found time using the y-axis, and this time it's not going to be any different. So we have xf is equal to xo plus v initial t plus 1/2 a t squared. I'm going to get rid of all my zeros. Okay, so we got 0 is equal to xo, v initial is also 0 plus 1/2 a t squared. Now I'm going to substitute in my my variables. Okay, so here, even though we said xf is 0, let me put that xf back in there actually. Erase. There we go. And the reason why I want to do this is because they tell us our height was h, okay, and so our displacement, right, xf minus xo, that's our height. That's the total vertical displacement. You could leave it at 0, but I just want to make a point here. Okay, so you could leave xf at 0, but my point is that the change in the vertical displacement, they're telling us as h, right, is equal to 1/2 a t squared. All right, I'm going to actually fix up this acceleration because we said our acceleration was g. Okay, so at this point, we can see what our relationships are. Remember, in order to see our relationships, you want to get rid of the variables that are not changing, our constants. We want to know what our new height is, so that stays. 1/2 is a constant. G is also a constant. We can get both of those out. We want to see how the change in the height affects the time that it takes to drop. Okay. Now here, I'm going to do a little side note, is a new type of relationship. This is what we call, so they're both in the numerator, so we know that they're directly proportional, but this is a directly proportional square relationship. Okay, directly proportional square relationship. And I think the best way to look at this relationship is to actually see how numbers are affected when you plug in different changes. Okay, so right here, what we're looking at is not a 1-to-1 ratio, but is a 1-to-1 squared ratio. All right. So let's try an example. If I increased my height by a factor of 4, okay, so we have 4h t squared. I want to know what goes in front of my t. Okay, and the best way to do this is to actually see what squared would give you 4, right? So I need to see what number squared would give me 4, and the number is 2, right? Because 2 squared would give me 4. Because this t, okay, even though we didn't adjust that t, technically, that t and the variable in front are in parentheses. Okay, so 2 squared gives me 4. And another way to approach this, so I'm telling you right now that the answer is 2, but is to actually solve it mathematically. Okay, so from here, what we can do, so we'll replace that with the equal sign, right? 4h is equal to t squared. Take the square root of both sides. Okay, so if I take the square root of both sides, I get the number 2. So 2 is my deciding factor, and that is how my t is affected, right? Because the square root of t squared just gives me t. All right, so that means that if my height increased by a factor of 4, my t has to increase by a factor of 2. It will take twice as long. So let's think about this conceptually. If we have a object that's released from a height known as h, okay, pew, it falls, it hits the ground. Let's say it takes, 10 seconds to fall from a height of h. Let's say we quadruple that height. So this is now 4h. What this relationship is showing us is that when it falls, okay, the time it takes to fall will be twice as long. So this will be 20 seconds instead of just 10 seconds. So here we have that relationship, this squared relationship. Okay, well technically it's, so if 10 seconds is equal to t, 20 seconds is equal to 2t. Okay, with substitution here. So 2 squared would give us 4. All right. Now, what if we increase the height by a factor of 9, 9h? All right. So I'll do my little sketch over here, not according to the scale, of course. So my new height is 9h. Therefore, the time this takes to fall, t, okay, will have to be the square root of 9. So my time would have to be increased by a factor of 3. So 3t. So it will take 3 times as long. So if my original time was 10 seconds, it'll now take me a total of 30 seconds to fall. Okay, if I increase my height by a factor of 9. Now this also works in the opposite direction as well. Knowing that we have a h is equal to t squared, so we can either do it this way. The same relationship is root h is equal to t, right? So we have two of the same relationship. If I were to increase, or excuse me, if I were to shrink my height by a factor of 4. So here, my height, so square root of 1 over 4, okay, I shrunk by a factor of 4. So root 4 gives me 1/2. Okay, so we're trying to keep that relationship there. So back to our original problem. If we, instead of saying h, we shrink it. Okay, we shrink the height to a quarter of its original size, a quarter of the height. Then if you shrink it that way, the time it takes to fall would take a half as long. So if the original time was 10, it'll take 5 seconds to fall. Okay, because we have the relationship here, that square root relationship. All right. Now, time for the actual question. Okay. So this is the relationship of how you can look at all of that. So we know that height and time have this unique square relationship, and that's one relationship that actually pops up often. Now, if we take a look here, it says that we still want to land at a distance d away. So therefore, how should we change our height? Right? How should we change our height? Now, this relationship alone isn't good enough. Because this horizontal distance, we can't use the y stuff to really solve for it. So let's figure out the relationship for the x direction. So we have VF is equal to VO plus A times T. We have XF, there we go, XF, XO plus V initial T plus 1/2 AT squared. All right, so here's the first one. We can't use that first one because it doesn't have the range. So here we have this equation. Once again, I'm going to substitute in my variables that I know. My final position, according to the problem, what did they say it was? It was D. Okay. Our initial position is 0, so I'm just going to leave it as it is. Our initial velocity, I believe they just called it V initial, right? And then we have time, and we have 1/2 AT squared. That A is 0, so that all becomes 0. So our relationship that we're looking at is the distance is equal to the velocity and the time. Okay, so we want to hit the same distance d away, but here's where it gets tricky. Okay, so this is our constant. Our constant is d. We want to know how to change our time, because we know our initial velocity is, I believe, double. Yeah, we have double the initial velocity. Therefore, how can we adjust the time? So if d is the constant, if our velocity goes up, our t has to go down by a factor of 2. Okay, so we need to have half the amount of time. Now, at this moment, you might get excited and be like, oh, that's an answer choice. Okay, but if you take a look at the answers, it wants it in terms of the height. And that's where we have to take this idea and go back here, right? So this is our height relationship. So I'm going to rewrite that relationship down here, h t squared. We also have root h is equal to t. All right. We know our time has to shrink by a factor of 2. So I'm going to use this right here. So if we know that our time has to shrink by a factor of 2, the square root of what number would give us 1/2. Okay, the square root of what number will give us this relationship that we just found, and that is the square root of 1/4 of the height will give us 1/2. So that is why we want to change our height by a factor of 4. So if we shrink our height by a factor of 4, the time it takes to fall will be a half as long. All right. Hopefully you learned a thing or two. This is a very tricky way of approaching these problems. It's doing math without actually doing any math. Yeah, if you have any questions, let me know. Otherwise, I'll see you next time. Bye-bye.